let's start today's material. So last time we learned the method of solving differential equation, some methods. One of them is reduction of order. Reduction of order tells you the second fundamental solution if you know the first fundamental solution. And we also learned the characteristic polynomial, which solves the second order linear differential equation with constant coefficients. And also we learned Cauchy-Euler equation, and there the characteristic equation is a little bit different from the characteristic equation of the constant coefficient linear differential equation, but basically the scheme is similar. So let's see some example here. So solving the Cauchy-Euler equation is not different from solving homogeneous differential equation with constant coefficient. For example, let's try to solve the first one. So here we have differential equation 3x squared y double prime plus 6xy prime plus y equals 0. So you have to notice that this is Cauchy-Euler equation. So the characteristic equation is 3 lambda lambda minus 1, 6 lambda plus 1 equals to 0. So when you expand this, this is 3 lambda squared, 3 lambda plus 1. So the roots are 6 minus 3 plus minus 9 minus 12. Okay, so this is 6 minus 3 plus minus square root of 3i. And when you have these complex roots, then fundamental solutions are, well, let me just put the general solution right away. So we have x to the minus 1 over 2x, don't forget x here, and cosine of square root 3 over 6 ln x plus c2x 1 over 2x and sine square root of 3 ln x. And one of the comment I want to make is you might ask, although there's no indication that y is a function of x, how do we know that the y is function of x? Y, I'm sorry, so this is not x, sorry. I got confused with the exponential, so that doesn't make sense, right? So how do I know that this function is in terms of x? The answer is you don't. You don't know whether this function is in terms of x or whether in terms of t or a, b, anything. But since I know that the x squared is in the equation, then I presume that this y is function of x and this derivative is in terms of x. So that's, I guess that my function y, the solution y, is in terms of x. If it's not in terms of x, then let's say this is derivative in terms of t, then this is not a Cauchy-Euler equation. This is just constant because x is independent to the variable t. So we can just consider x as independent variable, which means that I can just consider x as constant. So when I'm saying I want to solve this as a Cauchy-Euler equation, then I'm assuming that y is function of x. So we have this solution. And conversely, if you have a specific type of solution, you can guess that the solution satisfies some differential equation. So for example, in number 2, we are given with a solution of general solution of the form c1x 1 over 2 cosine 1 over 2 ln x and plus C2x 1 over 2 sine 1 over 2 ln x. The question is, find a homogeneous differential equation, which is Cauchy-Euler equation if you're looking at the form of solution, whose solution is of this form. So basically, this solution, you can guess that this is obtained from the roots of characteristic polynomial, and roots are of this form, 1 over 2 plus minus 1 over 2 I, right? So if you have these two roots, then quadratic equation having these roots are lambda square. Here we should have a lambda, so how I get the lambda is that, well, first of all, let's just start from the beginning. So these are roots, so the quadratic equation having these as roots is lambda minus 1 of the root, 1 over 2 plus I over 2, and the other is 1 over 2 minus I over 2. And this is the equation that having solution. And if I expand this, I get lambda square minus of 1 over 2 plus I over 2 plus 1 over 2 minus I over 2 lambda, and then plus of these multiple 1 over 2 plus I over 2, 1 over 2 minus I over 2, and equals to 0. So, and then if I expand this, then this is lambda square minus lambda, so this cancels out. And this becomes minus lambda. And here we have the multiple of complex numbers. Did you learn the multiple of complex number in high school? Okay. So 1 over 4, and this is plus minus, so you can just square minus square. Okay, so we have minus I square over 4. I squared is negative 1, so this is not 0. And we have lambda square minus lambda plus 1 over 2 equals to 0. And this is a characteristic equation of Cauchy-Euler equation. So this is not the final form of differential equation, because we have to make this into somehow this form, a times lambda minus 1 plus b lambda plus c. I want to find a, b, c, so that my differential equation is a double prime, a x squared y double prime plus b x y prime plus c y equals to 0. Well, you can guess that a is 1, so I need this term, and since I have minus 1 already, b is 0 and c is simply 1 over 2. So the final differential equation I want is x squared y double prime plus 1 over 2y equals to 0. So you can guess that this solution is come from this Cauchy-Euler equation. Okay. Any questions? Any questions? No? And let's look at third one. So third one is not actually Cauchy-Euler equation, but it says if you substitute y into x minus 4 to the power of m, you can solve this equation. So basically, I have x minus 4 y double prime and minus 5 times x minus 4 y prime and plus 9 y equals to 0. So my solution, this equation is almost similar when I replace x minus 4 with x. So almost similar, if I replace x minus 4 to x, then this equation almost similar to a Cauchy-Euler equation. So I'm trying to solve that the solution will look like x minus 4 to the power of m. Because in the Cauchy-Euler equation, I'm trying to find the solution of the form x to the m. Here, I'm replacing x with x minus 4. So let's plug in this. We have x minus 4. Is it square? Yeah, this is square. Square. 네, 감사합니다. 네. m minus 1 and x minus 4 to the power of m minus 2 minus 5x minus 4 m x minus 4 m minus 1 9x minus 4 m equals to 0. So we have x minus 4 to the power of m everywhere. So let's remove that. And what left is minus 5m plus 9. Right? So we have m squared minus 6m plus 9 equals to 0. So m is equals to 3, right? So that's double root. I need two fundamental solutions to find the general solution. But we only have 3. So how do I get the rest of the solution? So one solution is x minus 4 to the power of 3. And the second solution is now computed by the reduction of order, y1 square e to the minus. Now, it's important that what is p. So you have to make your coefficient of y double prime into 1 so that you can plug in p correctly. So this y double prime minus 5 over x minus 4 y prime plus x minus 4 square 9y equals to 0. So this is p. So minus 5 over x minus 4 is p. So we have plus 5 over x minus 4 dx. You can compute your second fundamental solution this way, but also you can simply look at the form, this form. So in the Cauchy-Euler equation, the second fundamental solution looks like ln of absolute value of x, right? So everything is, x is replaced by x minus 4 in this example. So you can guess that in this case, this is simply x minus 4 times ln x minus 4 will be the answer. And that is true. So therefore, the general solution is, so C1 x minus 4 cube plus C2 x minus 4 cube ln x minus 4, right? Okay, so problem 4 is just for your information that you can solve your differential equation, a Cauchy-Euler equation, just like the linear homogeneous differential equation with constant coefficient if you replace x with exponential functions. And just for information, this is not a fundamentally new thing because you can solve this differential equation easily by Cauchy-Euler formula. So any questions so far? Do you mean number 3 or number 4? The question is, why do we substitute that way? Do you mean 3? 3, because, let me explain again. So, if you're looking at this one, this given differential equation, this is almost look like, let's say I replace this, not lambda. Let's say I want to replace that with t, okay? This as t, this is as t squared. So then, what is dy dt? So instead of dy dx, I want to think about dy dt. Now, y is a function of x, but x is now a function of t because x minus 4 is t, so I can replace x with t plus 4, okay? So I can consider y as function of t again. So I can consider what dy dt. And what is dy dt? If you take the derivative of composite function, this is a composite of y and t plus 4 function. So this is simply dy dx. It's the same thing because if you take the derivative, first you take the derivative of outside function. Outside function is function of x, and you take the derivative of x, and you take the derivative of t of inside function, and if you take the derivative of t plus 4 by t, you get 1. So dy dt and dy dx is the same thing, okay? So if I replace this x minus 4 with t, what I get is t squared. And now this was actually dy dx, right? But we have dy dt exactly equal to dy dx, and the second derivative are the same because, again, x is replaced by linear function t plus 4. So this differential equation is now dy dt minus 5 t dy dt plus 9 y. So these y are now in terms of t. We are talking about the function in terms of t. And we are going to find a solution of this differential equation because that's exactly the same differential solution to the original differential equation. When you try to find the solution of this differential equation, you use the Cauchy-Euler formula, but basically what you're guessing is that your solution will look like t to the power of lambda, right? So I used m in this case, but this is lambda again. Now, what is t? So t is x minus 4 to the power of lambda, right? So we can go through these steps so that I can find the function of a solution of y in terms of t, and then after find the general solution, replace t with x minus 4, but I can simply start with y equals x minus 4 to the power of lambda as the form of solution to the given differential equation, and start right away find the solution using this formula. So it's exactly the same thing when I find the solution of this differential equation, because now y will be c1 times t to the 3, okay, plus c2 times t to the 3 ln t, and then replace that t into x minus 4. I have x minus 4 to the power of 3, c2 x minus 4 to the power of 3, ln x minus 4. Same thing, right? Okay, let's move on to the next one. Now we need two more methods of solving differential equation. One is method of undetermined coefficient, and the other is method of variation of parameter. And these two methods, from now on, is finding a solution of non-homogeneous differential equation, and this is finding a particular solution of non-homogeneous differential equation. Okay, so first, method of undetermined coefficient start with a differential equation with non-zero non-homogeneous term fx here. Okay, and then be careful that the coefficient in the differential equations are all constants. So this, I'm sorry. So of undetermined coefficient are now a differential equation of the form whose coefficients on each derivative are constant, and there is non-zero non-homogeneous term fx. Okay, and this is a method of solving a particular solution. It's finding a particular solution. Okay, it doesn't solve the general solution. General solution appears from the general solution of homogeneous differential equation from the principle of superposition. We're going to talk about that later with the example. So what's the method? So basically this method is based on try and error. I just try some candidate of particular solution, and if it doesn't work, then I try another example and another example. So the type of example, type of solution that I'm trying to guess is depending on the type of function that appears on the non-homogeneous term. For example, if you have f equals to constant, then my guess of the particular solution is a constant solution, but I don't know what constant that should be, so I just start with yp equals to a, and then find the a satisfying this differential equation. And for example, if my non-homogeneous term is quadratic equation 3x squared minus 2, then I have to guess my particular solution as quadratic equation. So one important thing that you have to be careful here is that even though in the non-homogeneous term has no x term, I should put the x term in my guess because I need to try the most general term of quadratic equation. So I need a, b, c to determine. And also, if I have exponential function with 5 inside of the coefficient of exponent, then I should try with the same type of function, but with the unknown coefficient a. Okay, that's the other thing. So 5 is already given. So if I change 5, I get totally different function. If you have two exponential function with different coefficient in the exponent, then they are not linearly independent. You cannot transform one function to the other by simply multiplying the constants. So this is the form. This is the only form that you can guess. And if you have a sine function or cosine function with the coefficient inside, then you have the same sine or cosine with the same coefficient here. But also important thing is that even though you only have sine inside of the function f, you have to guess cosine and sine. Okay. The reason why you have to guess both is that although sine and cosine are linearly independent, when you take a derivative, cosine becomes sine and sine becomes cosine. and we are trying to solve the function satisfying the differential equation. So sine may appear from the first order derivative of cosine, right? Or a second derivative of sine, and this might intertwine each other so that if you start with the only sine function guess, then you may not have a solution. So you need cosine sine, okay? And there are more applications here. So if you have a mixed term, such as e to the power of 3x and cosine, you have to start with e to the 3x times of this cosine form. So don't think about the actual formula of fx. Think about the type of function. So you have exponential function multiplied with cosine function, sine function, okay? And then your guess of yp must be exponential function times sinusoidal function. So most general form that you can guess for sinusoidal function is that this above form. So this appears because of the line right above here. And if you have a polynomial times exponential, then you also have the polynomial type and exponential function. And since this is a first degree polynomial, you have to have first degree polynomial function in the general form of yp, and so on. So, for example, if you have degree 2 polynomial times the sine, then you have to have a degree 2 polynomial, general form of degree 2 polynomial times the general form of sine function. So I divided it into two parts, but you can take it into one, so that the degree 2 polynomial has ABC terms and sine function has DC constant terms. I'll explain that later. And also, if you have a mixed of three types of function, one is the polynomial and the other exponential, and cosine, you have to take these all into the count at the same time. So first you have the degree 1 polynomial and exponential, and also you have the sinusoidal function, most general form. So let me give an example here. This is a simple example. Find a complementary solution and a particular solution, and that gives the general solution. So it also says to use the third principle of superposition 3 to find the general solution. So I will do this by hand for now, but if you have a complicated complicated f, then it's really hard to find the correct ABC by hand, because it might take 5 equations to solve or 6 equations to solve. So later I'm going to teach you how to use the MATLAB to find the exact coefficient to ABC. Now let's see y double prime minus, let me write it bigger. So y double prime plus 2y prime equals to 2x plus 5 minus e to the minus 2x. So what's the third principle of superposition? It says that if you split your f into sum of two f's, okay? So f1x is 2x plus 5, and f2x is minus e to the 2x. Then you have two separate differential equations. One is y double prime plus 2y prime equals to f of 1x, and y double prime plus 2y prime equals to f2x. Now, suppose that we solve this differential equation separately and found two particular solutions for each differential equation. Okay? And then a particular solution of given original differential equation is simply the sum of these two particular solutions. That's the principle of superposition 3. So I'm going to find this yp1 and yp2 separately. So if you're looking at the this differential equation, the non-homogeneous term is degree 1 polynomial. So I can guess my yp1 is degree 1, general form of degree 1 polynomial, ax plus b. Okay? And then try to solve AB by plugging into the differential equation. So when I take a derivative, second derivative of yp, it's 0 because this is first degree polynomial. And when I take the first order derivative, then I get a, so I get 2a on the left hand side, and on the right hand side, I get this 2x plus 5. Now, I'm guessing that this is the solution, which means that the left-hand side and right-hand side must be identically the same function. It's not that I can find a single x that satisfies this equation. It should be the same function identically. So on the left-hand side, it says it's a constant function. And on the right-hand side, it says it's a degree 1 polynomial. They cannot be the same function, obviously. They are not identically same at all, because whatever value of a I choose, this is a constant function, this is a degree 1 polynomial. So there's no solution, there's no such a that satisfies that yp1 is the solution to this differential equation. Is that it? No, because this is only a guess. This is only a guess that I can find this solution. So it simply means that my guess is wrong. Okay? So what happens? What if my guess is wrong? So your guess will be wrong in many times. Just multiply x and do it again. Multiply x and then plug into the differential equation to find the solution again. So my second guess of yp1 will be ax plus b times x. So in other words, ax squared plus bx. Now, important thing is, if this is not the general form of quadratic equation, I don't have plus c. Although this is okay because I came up with this candidate from the failure of the first degree 1 polynomial. If I had the second degree polynomial for the non-homogeneous term in the beginning, I should have started with the general form of quadratic equation. But this is the first degree polynomial. So I tried, but I failed. So it's okay, just start with the multiple of x. Okay? So start with this one. I have, let me erase this. So if I take a double derivative, I get 2a. So 2a plus, so this is y prime, y double prime, and 2y prime, and y prime is 2ax. So it's 2ax. And that must be equals to 2x plus 5. I'm sorry, so I forgot b, right? I forgot b. So this is 2ax plus b equals to 2x plus 5. Okay. And then I get 4ax plus 2a plus 2b equals to 2x plus 5. Now, these two functions must be identically the same. So that means 4a is equals to 2, and 2a plus 2b equals to 5. So this implies that a is 1 over 2, and this implies that b is 2, right? So I have AB uniquely defined. So if I had yp equals to 1 over 2x squared plus 2x, then this is the particular solution. So I found one particular solution again. So let's keep that. So let's keep it here. So let me just erase this. So this is simple this is simple system of equations. So you can find your ABs easily. X squared plus 2x. And let's try to find yp2. So yp2 have a form similar to e to the negative 2x. So we start from a times e to the negative 2x. And try to plug in here. The second order derivative has negative 2 squared a e to the negative 2x and minus, plus 2 of minus 2a e to the negative 2x. And that must be equals to minus e to the negative 2x. And simplify this. What you have is, again, well, these two cancels out. This is 4 and this is minus 4. So this left-hand side all becomes 0. And this is not a zero function. So again, what we have is a failure. So this fails. It fails. So what do we do when we fail? You multiply x. So you start with new guess, a times x e to the negative 2x. You always multiply x, regardless of which type of function you choose for the guess. Just apply x when you fail. And then, now the derivative is a little bit complicated, so let me write down the process here. When I take the first derivative, I get a e to the negative 2x plus a x times negative 2 e to the negative 2. And yp2 double prime is minus 2a e to the negative 2x plus a minus 2 e to the negative 2x and minus plus ax minus 2 squared e to the negative 2x. So let's plug into the here. Okay, so we have combining these two, I get minus 4a e to the negative 2x, and here we have plus 4ax e to the negative 2x, and 2 times y prime becomes plus 2 times a e to the negative 2x minus 2ax e to the negative 2x, and that must be equals to e to the negative 2x. Okay, so let's look at these ones. What we have here is, it seems like it's purely by luck, but it's not, because that's how we get the, that's why we actually multiplied x here. You see that 4ax is cancelled out with the minus 4ax right here. So we don't have x e to the minus 2x terms, which doesn't appear on the right hand side. So what we have is minus 4 plus 2, so minus 2a e to the negative 2x equals to negative e to the negative 2x. So therefore we have a equals to 1 over 2. So our second solution, yp2, is 1 over 2x e to the negative 2x. So we have two solutions. We have these two solutions. So what's our particular solution to the original solution? Just the sum of these solutions. 1 over 2x squared plus 2x plus 1 over 2x e to the negative 2x. Okay? Now this is not over, because the question is finding the complementary solution and the particular solution. So what's the complementary solution? Complementary solution is when you replace your non-homogeneous term into 0, and the general solution is the complementary solution. So when Px is 0, our differential equation becomes homogeneous differential equation with constant coefficient, which is y double prime plus 2y prime equals to 0. You can solve this by characteristic equation, which is lambda squared plus 2 lambda equals to 0, which has solution as root 0 or minus 2. So therefore, the complementary solution is a combination of two fundamental solutions. One is e to the 0 times x, and the other is e to the negative 2x. So e to the 0 times x is just a constant 1, right? So we have c1 plus c2 e to the negative 2x. So this is the complementary solution. And combined with the particular solution and complementary solution, the general solution is y equals to c1 plus c2 e to the negative 2x plus these terms, 1 over 2x squared plus 2x plus 1 over 2x e to the negative 2x. This is the general solution that you have to write if the example asks you to find the general solution of this differential equation. And I think the most of the questions in the homework is similar form. So you have to show this all process. So there's a way you can avoid this complicated computation. One is simply using the MATLAB, or you can slightly minimize your computation if you start with the solution, this complementary solution. So this is a side note, but you have to be careful to understand what that means. So first, if you're looking at the complementary solution, you have a constant solution and e to the negative 2x solution here. Okay. So when I try to find the particular solution of these two differential equations with non-homogeneous terms, I guessed that my first particular solution is the first degree term here. But you see that the first degree polynomial has constant term here. So that means if I combine that constant term with this arbitrarily constant, this constant term, well, not actually this term, so let me write it here. So yp1 ax plus b was our original guess. And this term has no effect in the general solution of this differential equation because of this c1 term. Because even though I specified b, there is an arbitrary constant c1. So if I take b plus c1, it just means an arbitrary constant. So there's no meaning of finding particular b satisfying this differential equation. So that's why this actually failed, because since b has no effect of finding a particular solution, what I'm really doing is that I'm just trying to find the particular solution of the form ax, and this is not enough. So for solving the particular solution of second order differential equation. And also, if you're looking at the second particular solution, our first guess of second particular solution, I started from a times e to the negative 2x, and e to the negative 2x already appeared in here. So even if I specified a, that has no effect because this will be absorbed in this arbitrarily constant c2, right? So basically I'm doing nothing here by guessing my particular solution. So by looking at the complementary solution, you can guess at the beginning, before you try to plug in this and these solutions to the each differential equation, that you can guess that this may not work because of this fundamental solution to the complementary solution. So that in that way, you can skip the first guess and then start from the second guess that applying the x on each side. So any questions? Okay, no question. Okay, so that was one of the method. Another method of finding a particular solution. Okay, so here's a question. Log. So when you have a log in the non-homogeneous term, you don't use the method of you don't use the method of undetermined coefficient. Log is not the case. So if you have a log in fx, you don't use undetermined coefficient. You have to use another method. So undetermined coefficient method only works for constant polynomial, including constant or exponential or sinusoidal functions, or mixed of those functions, not log functions. The good questions. So maybe if you have a log in your non-homogeneous term, you might be able to use the variation of parameters that we're going to talk about it right now. So it says the following: if you have a second order differential equation with non-homogeneous term, and suppose that you know the complementary solution of this differential equation. So y1, y2 is the solution to this differential equation when this rx equals to 0. Okay, and let's say w be the Wronskian of y1 and y2. So you recall what Wronskian is, that it is the determinant of 2 by 2 matrix with specific coefficient entries, and we use that Wronskian to find out whether two functions are linearly independent or dependent. If the Wronskian is non-zero, then y1, y2 are linearly independent, so that we can use those functions as fundamental solutions. So in the assumption that we says y1, y2, linear combination of y1, y2 is the complementary solution, so y1, y2 are assumed to be the linearly independent functions. The conclusion is, if you want to find a particular solution with this non-homogeneous differential equation, you can take a u1 and u2 right here, u1 and u2, and then multiply with y1 and y2, and this form can be a particular solution to this differential equation if y1 prime is given by this formula and y2 prime is given by this formula. It might be confusing where y has a negative on the first line and there's no negative on the second line. There is a consistent way of memorize this formula. Basically, this the last two lines are obtained by this formula. So this one is the formula. Okay. So I will show you why this works. Before we actually go through why this works, you have to at least memorize this formula to apply the method of method of variation of parameter. So y1 prime is the fraction of the two determinants of 2 by 2 matrix. On the numerator, you have 0r. You have 0r on the first column, okay? And the denominator is the Wronskian. And the u2 prime, you have 0r on the second column, okay? Because this is the second u2, second u, you have 0r replaced in second column and the same Wronskian on the denominator. And see, the rest of the column are exactly the same columns from the Wronskian. You see, the numerator on u1 and u2 are simply the determinant of matrix where the first column and second column of the matrix is replaced by 0r from the 2 by 2 matrix. Okay? In that way, you can memorize it better. I think it's better to look at the example and then explain why this method works. So let's look at the example here. Y double prime plus 4y equals to tangent squared 2x. Okay, find the solution. Find solution means find the general solution. Find the most general solution. Okay. So recall that the method of variation of parameter assumes that you know two fundamental solutions of homogeneous differential equation. So you have to find y1, y2 as fundamental solution to the homogeneous differential equation y double prime plus 4y equals to 0. So you can solve this solution differential equation using characteristic equation y squared plus 4 equals to 0 and y is plus minus 2, lambda is plus minus 2. So therefore, you can guess your y1 as e to the 2x. Actually, this is a solution, not guessing. Okay, y1 is e to the 2x, and y2 is e to the negative 2x. So these are fundamental solutions. Now, so my particular solution, yp, is of the form u1, y1 and u2, y2. And the variation of parameter says that u1 prime is now equals to 0r y2 prime over y1, y2, y1 prime, y2 prime. And u2 prime is equals to y1 prime 0r of y1, y2, y1 prime, y2 prime. Now what's r? In our example, it was already set that the coefficient of y double prime is equals to 1. But when you try to find r, if you have a if you have a coefficient of y double prime not equals to 1, you have to divide your coefficient on both sides so that it becomes 1. So in here, it's already set to be 1, so this is our r, rx. Okay? And it's very important that if you set y1 as e to the 2x, y to e to the negative 2x, you have to keep the order. This y1 and y2 are should be applied with the same order. So you cannot mix these two inside of this formula. Okay, so if you choose y1 to be e to the negative 2 and y2 to be e to the 2x, then keep that order inside of the formula. Don't mix up in this formula. So let's compute this. You have lambda 2. Oh, yes, right. Yeah, sorry. Sorry. 2i. So we have cosine 2x and y2 sine 2x. Okay. Again, you can choose y1 as a sine and y2 as cosine. That's okay, but do not mix that order inside of this formula, u1, u2. So here we have tangent squared 2x as r, and y2 is sine 2x, and the square derivative sign is 2 times cosine 2x, right? And here we have cosine 2x and sine 2x minus 2 sine 2x, 2 cosine 2x. Before I compute u2, let's finish this computation. So on the denominator, we have cosine square minus sine square, right? So it's a cosine square plus sine square with constant 2. So we have 2. On here, so 0 times 2 cosine is 0, and negative of tangent square sine. So we have minus sine square, sine 2x, tangent square 2x. And that's our u1. So important that this is not u1 itself, this is u1 prime. Okay? If you want to find u1, then you have to take integral again. Well, let's finish with u2 prime. So the denominator is same as u1, so you get 2. On the numerator, we have y1 times r, and y1 is cosine 2x, and r is tangent, so cosine 2x tangent square 2x. So let's try to find u1 first. So u1 is integral of 1 over 2 times sine 2x, and let's rewrite that into cosine square 2x over sine square 2x. I want to replace this cosine. Okay. Let's say replace cosine 2x as t. Then I get dt equals to minus 2 sine 2x dx. So I have sine 2x dx. So that will be replaced with negative 2 dt. Okay. And I also have minus 1 over 2 in front. So what I have in the rest is t squared. And here this is 1 minus cosine square, so it's 1 minus t squared. Okay. So let me write it here. So we have u1 is equals to negative to 1 over 4 times of integral 1 over t squared minus 1 dt. and that is 1 over 4 minus 1 over t minus t. Okay, so I don't have to put the constant c plus c here. What if I put the plus c? Then this u1 inside of u1 there will be plus c inside, and that will only make c times y1. Okay, and c times y1 is already appears in the complementary solution. This is only we are only finding a particular solution. What appears in the complementary solution will be in the complementary solution, so we don't have to worry about plus c times y1, so we don't put the plus c here. So this is minus 4t minus 4t, and t is cosine 2x, so replace that in 4 cosine 2t and minus 4 cosine 2x here. So that's our u1. Now what about u2? So u2 is integral of 1 over 2 cosine 2x cosine squared 2x sine 2x dx. And then, well, let's cancel this out. So we have 1 over 2, 1 over 2, and then let's replace cosine again. That makes sense? Maybe not, just let's replace this first. So replace sine square with cosine 1 minus cosine square and cosine 2x dx, and that becomes 1 over 2 of cosine 2x over 1 minus cosine 2x dx. So this is secant x. Let me erase this. Do you remember the formula of integral of secant x? So I don't really remember the formula, so I think the method was, no, it actually, what was the formula of integral of secant x? We have to multiply something on the numerator and denominator. So secant 2x tangent 2x plus secant 2x. Secant tangent. Secant tangent derivative. Let me make sure that, yeah, secant tangent, right? Let's compute that. Okay. So tangent 2x plus secant 2x dx minus 1 over 2 cosine 2x dx. So we have u1 here, so let's erase this. When we do this, we have, if you take a derivative of tangent, you get secant square. You have to take a derivative of secant 2x, we have secant and tangent. Although I think you have to replace 2x with t. So if you replace 2x with t, everything goes to t. And dt is now d2x, 2dx. So dx will be 1 over 2 dt. So this is now 1 over 4 times ln of tangent 2x plus secant 2x. And minus 1 over 4 sine 2x. Right? So that's our u2. That's our u2. So what is yp? Yp is u1, this guy, times y1 cosine 2x. So there's a canceling. So minus 1 over 4 minus 4 cosine squared 2x. And u2 times y2. So this is sine 2x over 4 ln of tangent 2x plus secant 2x, and minus 1 over 4 minus 1 over 4 sine squared 2x. Okay, I think it's right. So there's no more. Well, you can simplify a little bit more, but basically you can. This is it. Well, so you can combine these two, but still the cosine parts survive. So this is up to you. So this is the particular solution, and this is not it. So this is not the final answer, because we want to find the solution, which means that we want to find the general solution. So general solution, y, is the complementary solution plus the particular solution. So complementary solution is C1 times cosine 2x, C2 sine 2x, and minus, and particular solution is this blah blah blah. We have sine squared 2x plus 1 over sine 2x ln tangent 2x plus secant 2x. And this is our answer. So we are almost time, but so I didn't still explain why this variation of parameter works. So far, do we have any questions? U1에서 40? Oh, why did it become 40? Yeah, you're right. This is T over 4. Ah, okay, so that makes sense then. This is actually 1 over 4. Then the n becomes combined together. So yes, you're right. So you have minus 2 minus 1 over 2 plus this guy. So yeah, thank you. So I had a mistake here, and also there was a mistake in 1 over 4 here. So I want to emphasize that if you have a complaint, on homework or quiz, and you think that the score was not fair because of the small mistake, then please let me know. I'm not taking points off because of the small mistake, like this one's small algebra mistake or small very minor mistake. I'm not that picky on these mistakes. 만약에 나중에라도 숙제나 퀴즈나 시험에서 점수가 깎였는데 이제 답지랑 비교했을 때 뭔가 내가 되게 사소한 실수를 했다. 그냥 숫자 계산을 잘못했다거나 뭐 그런 거에서 뭐 밀려 썼다거나 그런 것 때문에 점수가 깎였으면 말을 해주세요. 그런 것 때문에 점수를 깎지는 않거든요. 제가 보고 실수할 수도 있으니까. Okay, so let's start with yp. So I'm trying to explain why we have this formula. And I want this to be the solution of y double prime px y plus qx y equals to rx. Okay. So let's try to take a derivative. We have y1 prime, u1 prime, u1, y1 prime, and u2 prime, y2, and u2, y2 prime. And the second derivative is u1 double prime, y1, 2u1, y1 prime, u1, y1 double prime, and same thing here, u2 double prime, y2, 2u2 prime, y2 prime, and u2, y2 double prime. And let's plug into the differential equation. So this part just goes here, okay? So for y double prime, and plus px times, let's write this, u1 prime, y1, u1, y1 prime, and u2 prime, y2, and u2, y2 prime, and plus u1, y1, u2, y2 equals to r, okay? Now it seems very long equation, but I'm going to simplify this. First of all, let's combine all the u1 terms, okay? So here u1, if I take the term, I will cross out that term. So u1, so y1 double prime. And how about u1 here? So we have px times u1, so just py1 prime. And also there's u1 here, and plus, qx. It's qx multiplied here. So this is q times y1. And how about we combine u2 here, y2 double prime, plus u2 here, py2 prime, and u2 here, qy2. Okay, and let's combine the rest of the terms. Here u1 double prime y1 for here, and 2u1 prime y1 prime, and u2 double prime y2, 2u prime y2 prime, and here we have pu1 prime y1, pu2 prime y2. That actually equals to r. Okay, but you see, this parenthesis, the term inside parenthesis, is 0 because y1 is a fundamental solution to the homogeneous differential equation. So when r is 0, y1, y2 are solution to this homogeneous differential equation. So these are 0. These goes to 0. So what we want is the u1 and u2 satisfying this equation. Okay? But let's look at this one. So if I take p part, this is my term, and let's say let's call this star, okay? And then let's see what happens when I take the derivative of this expression, okay? Then I get u1 double prime y1 and u1 prime y1 prime. And for the second term, it's u2 double prime y2 and u2 y2 prime. It's very similar to this term, right? So here we have this term, and also although this is coefficient 2, we have same term, and also same term here. So here's the condition. We want to find u1, u2 satisfying this equation if this star part is 0. If this star part is 0, then we only need to solve this part equals to r, right? Equals to r, because I assume that this is 0. But then, since this term appears because of this derivative of star, these are already becomes 0 if I assume that star is 0, right? The derivative of 0 is 0. So this is, if this is 0, then the rest of the term is one of this u1 prime, y1 prime, one of u2 prime and y2 prime. Then what we need is u1 prime and y1 prime, u2 prime, y2 prime to be equals to r. So here's the assumption. We have star wants to be 0. If we have star equals to 0, then in order to solve this equation, we only need this equation. But what it means is that I need, if there is a solution of this system of equation, u1 prime y1 plus u2 prime y2 equals 0, and this equation u1 prime y1 prime and u2 prime y2 prime equals to r, then we are done. Because we assume that this equals to 0. This comes from the star equals to 0. And this equation from our assumption. If these two are satisfied, then we can solve this differential equation. We can solve this u1 and u2 satisfying differential equation. But you see that the u1 prime and u2 prime appears in both equations, and you can consider y1, y2, and y1 prime and y2 prime as a coefficient, right? So let's just try to solve this using the method that you already know for solving system of equations. So first take so let's say this is equation 1 and this is equation 2. Multiply u2 on equation 1 and subtract u2 prime on 1 and u2 on 2 side by side. What you get is y1, y2 prime minus y1 prime, y2, u1 prime, and that equals 2 on the right hand side minus y2r. Okay? So therefore, you get u1 prime equals to y1, y2 prime, y1, y1 prime, y2 minus y2r. But that is equals to each numerator and denominators are equals to the determinant of 2 by 2 matrix. y1, y2, y1 prime, y2 prime. And 0r of y1, y2. y2, y2 prime. Right? And do the same thing for solving y2. You can multiply y1 prime on the first equation, subtract y1 times the second equation, then you get the solution, expression of y2 prime, and so on. So that's how you get the variation of parameter. So later, if you move on to the linear algebra in next year, you will learn that this method is actually the particular example of Cramer's rule, that you can solve your system of equations using the determinants of n by n matrices. Okay, so I think that's it for today, and that's it for this week. And I think that's that. So far we covered chapter 2 up to chapter 2 section 7. So until 2.7 we covered the material. So there is on 2.4 there is a spring motion. We are going to talk about that in the next week. So if you need further context, read the book and ask questions. Any question before we do the MATLAB? Any questions? 과제. So homework is already up in the LMS. We're going to have a quiz on next week. And I'm not going to tell you whether it's on Monday or Thursday. So it could be the next lecture. Okay, so I'm going to tell you how to use the MATLAB when you solve the differential equation, particularly if you're trying to solve the homework problems. I'm not asking you to write entire detailed lines by line computation in the homework report, because you have to type it. It's it's too much work to type all the details, but just type the important parts, and if you're done by your hand, show it, but you can skip your work using if you use the MATLAB. Just show your lines that you used in the MATLAB. So for example, let's try to find a solution to this differential equation right here. So here, y double prime plus 2y squared plus 2y equals x plus 3 times exponential of x. To find the solution, you have to find the complementary solution first. So I'm trying to find the roots of, for simplicity, let me write lambda as t. So t squared plus 2t plus 2 equals to 0. I want to find exact solution, exact root. And this root will be, I think it's complex root. So to solve solution exactly, 2 times t plus 2 equals to 0. So this is the equation, okay? So I put the double equal sign here so that it represents an equation, okay? So single equation symbol means that I'm plugging 0 to the left-hand side, but if I put the double equal sign, then it means equation. So when I execute this, so I have an answer. It says the root of this equation, so solution minus 1 plus minus I. Okay, so I can guess that my y1 is exponential minus x times cosine x, and y2 is exponential minus x sine x. Okay, so this is fundamental solutions. I want to find next particular solution. So let's say sims A, B, C. Yeah, and then let's say I have a yp as a times x plus b plus c times x. I'm sorry, so x is also should be considered as a symbolic variable. So I start with this expression. So I could split the yp1 and yp2. Well, you can do that. So let me do that in two ways. First, I define yp1 and yp2 separately. Okay, and I'm trying to solve my a, b, and c. So let's try to solve the a and b first. So the differential equation says diff yp1 in terms of x and double derivative is represented by the applying diff command twice. You get the yp double prime. So you see, if I execute this line, right? So I get x0, right? So this, since yp1 is a degree 1 polynomial, if I take a second derivative, you get 0, okay? And then plus 2 times of derivative of yp1 in terms of x, and plus 2 times of yp1. So when I execute this, I have this formula, okay? So this is the left-hand side of this equation when I plug in yp1 of the general form ax plus b. And I want this to be equals to x, right? So this is the solution, particular solution of y double prime plus 2y equals to x. And this is the particular solution of 3 times x, okay? So I want this to be equal to x, okay? Now, I also put the double equal sign here, okay? And this represents equation. So equation 1 is, was say, my equation is this one. So let me just show you the result. So equation is defined to be the equation. Okay, so this is not a formula, this is an equation. So the result is true or false. Okay. Now, to find a and b satisfying this equation for every x, I have to plug in some values of x, for example 0 or 1. So if I replace my x with 0, I can use this command, subs command. So this is the abbreviation of substitution, and it means that give the result of the equation after substituting the variable x with the value x. So that's the command, how you use the command. And you get this result. Okay, so this is, you see, also another equation. Okay, so let's say I call this equation 1. And that's not enough. I need another equation. I need to substitute x by another value, say 1. So this is the equation 2. Okay, so basically I have two equations. So equation 1 and 2. Okay, so here equation 1 is given by this equation. This is obtained by substituting our differential equation after replacing the y as yp1 and replace x by 0, and the second equation obtained by x by 1. And I want to find a and b satisfying these two equations simultaneously. So how do I find such a and b? You take solve command again, equation 1 and equation 2. So basically the result shows you the answer, not clearly and not explicitly. It says the answer is some kind of a structure element with this kind of fields. So the reason that this shows this type of example and this type is that I didn't specify what variable I'm trying to solve this. So well, same answer, sorry. So the same thing here. So in order to actually find out exact value of this solution, let's save this result after the solution command to the t. Okay, so t is just a variable, any variable. And if I want to retrieve the value of a and value of b, I can just simply take t dot a, t dot b. Okay, so when you're looking at the workspace here, t is 1 by 1 struct. Okay, so if you double click your t, here is the value of t. So content of the t is there. It has two fields, a and b. Okay, and both a and b are symbolic values, so it doesn't give you the answer in this window. But however, you can retrieve your value of a by taking this command, t times a and t times b, t dot a and t dot b. So it says a is 1 over 2 and b is negative 1 over 2. Okay, so answer that here you have yp1 equals to 1 over 2 times x plus minus 1 over 2. Okay, and how about yp2? So here yp2, you do the same thing, but let's do it more simply. We have yp2 and yp2 all replaced here, yp2, and this is now 3 times of x per p, right? This is our equation, and I want my solution equation to be obtained by subs equation x by 0, and then so this is a auto completion. So okay, so and then subs equation x by 1. Okay, and then also when you do this, now t has one field, only one field, so there's no need of distinguish the multiple field because there's only one. So it only contains symbolic value, which is 3 over 5. So it says t is 3 over 5, so which means that my c, so when I do this solve, there's only one unknown variable in these two equations, which is c. Okay, so I'm trying to solve c, so c is simply 3 over 5. Okay, so we have c equals to 3 over 5. So I have yp2 equals to 3 over 5 x power 3x. Is it? Just x, sorry. So I found two particular solutions, and I already know that my fundamental solutions are of this form. So I have y as c1 times this guy plus c2 times this guy. So I didn't put the star sign here because this is just a comment. So I don't need to be very precise. And then plus 1 over 2 times x minus 1 over 2 plus 3 over 5 times x by x. Okay, so this is our general solution. So I'm telling you that you can either do by your hand and show the computation process into your report, or you can use MATLAB to find the same solution. In that case, just attach your command in the report so that I can be assured that you did your homework by yourself. Okay, how about undetermined coefficients? So here we had y double prime 4y plus tangent equals to tangent square 2x. That was our question, right? The last question. Let's try to do this by MATLAB. First, let's start from, we know that the solution is, complementary solution is y cosine 2i and sine 2i. Sine 2x, sorry. And I want to find u1 prime, and let's say u1p is determinant of 0, y1, right? So I didn't define y1 yet. So it's cosine 2x, and y2 is sine 2x. And I'm always assuming that my x is symbolic variable. So define x as a symbolic variable. 2 times x. Sorry, it's 2 times x. Okay. And 2 by 2 matrix is given by this the bracket 0, y1, and r is tangent 2 times x squared, and y1 prime, which is differential x. Okay, so this is the numerator, the determinant of this, and divide that with I'm sorry, so this is y2, sorry, should be y2, and then y1, y2, and diff y1x and diff y2x. So if the line is too long, you can separate line with 3 dots here. So if you put the 3 dots at the end of the line, then what comes on the next line will be joined with the previous line. Okay, so with these 3 dots, MATLAB considers these 2 lines as one single command. Okay, so this is one of the tip that you can use. So this is a U1P. So if you take the result, and this is our result, and you see the denominator didn't simplify it because it simply computes the entire line here. So you can make it simpler by using simplify method. So then you have more simpler formula, right? Simplify. It's 2 times, well, it just made this way. So anyway, so let's take an integral of u1 prime. So u1p integral x. So that's our u1, right? So that's our u1. So this is our result. Okay, 4 times cosine 2x. And let's do the same thing for u2 prime. Just copy and paste. Here you have y1 instead, 0, and diff y1x and r, right? And u2 is integral of u2 prime in terms of x. So you have u2, well, it says given by arctangent of hyperbolic tangent of something. Y1. Nothing wrong here, right? So we have u2 prime equals to. So there are other methods. Maybe there are other methods of finding solutions. So anyway, yeah, u1 and u2. So we have yp equals to u1 times y1, u2 times y2. So that's our yp here, right here. Right here. Okay. So I think it could be a little bit simpler. So maybe this cosine part and cosine square part and sine square part can be combined. So if I take the simplify command again, yeah, that gets a little bit simpler. So minus 1 over 2, and I think this part is something like a log of something if you replace your arctangent, hyperbolic tangent with some log functions. Okay, so this is also a root. This is another form of solution, just using different functions. Okay. So do you have any questions on homework? If you want to do the homework with MATLAB, I can do this right now. So I'm going to upload this code to the LMS site, and you can simply open your MATLAB file with MemoPad. It's simply a text file. You don't have to install MATLAB in your computer to open the M file. Just open the M file using MemoPad and then copy paste that code to the MATLAB online website, and then that works. Any questions? Okay, if there's no questions, let's call it here. Have a nice lunch and see you next week.